continuing with section 1.8. So note that when we have a matrix like this, 1A01 means that here we can have any number. Then the transformation given by T of x is equal to A times x, where A is this matrix, this type of matrix. Then it is called a shear transformation. So what is the shear transformation? What happens in a shear transformation? Some points, or the points on a certain axis, they stay where they are, but all the rest of the points are shifted parallel to that axis to a new place. So example 3, let A is equal to 1, 3, 0, 1. Define the transformation from R2 to R2 by T of x is equal to AX. Find the images of the corner of the square defined by the lines, these ones. X is equal to 0, y is equal to 0, x is equal to 2, and y is equal to 2. Draw the square and its images. So we will draw them actually on the same plane and same axes. So the axes, we will call them x1 and x2. And here is the square. So remember, we had x is equal to 0. This line, x is equal to 0 means a vertical line. So it is this line, the x-axis. That is x is equal to 0. This one is x is equal to 2. This one is y is equal to 0. And this line is y is equal to 2. So we have this square. The points that will be, whose images we are going to check are, so this has coordinates 0, 0. This has coordinates 2, 0. This one has coordinates 2, 2. And the C has coordinates 0, 2. So we will be checking how these points shift, or where do they shift. So one by one. So at U 0, at O, now I'm thinking of this as a vector. So U will be equal to 0, 0, the vector which starts at the origin and it ends at the origin, which is the 0 vector. So when we apply the transformation to this one, to U, we get back our 0, 0 vector, because what we do, we multiply the vector with the matrix A, and we end up getting 0. So the O point stays where it is. Now the A point, so when I multiply the matrix with the A vector, which is the vector 2, 0, I get back 2, 0. So which means A is fixed. So all the points on the x-axis between O and A, they just stay where they are. At B is this point obtained from by, over there. So this point 2, 2, so the vector here is the vector 2, 2. I am giving them names, each of them. First was U, second was A. This one I call it B. So when we try to find the image of B under the transformation, we are getting 8, 2. So the point B goes to 8, 2. And the point C, which is the vector 0, 2, it moves to 6, 2. So here, down here, I have drawn again the square, and the point O, the point A, and the point B, which was over here, and C was here. Now B has shifted to a new point B dash, and C has shifted to a new point C dash. And then, so my square now looks like a parallelogram. So this is how we do these we apply these shear transformation. Okay, let's look at the next example. Okay. So this was example 3. So example 4. Okay, before we do that, note here that the matrix A, which looks like this, cosine of theta minus sine theta cosine theta, the transformation which chooses this matrix A is called a rotation. So it rotates the it rotates the figure or whatever, all the points by the angle theta in a clockwise direction, anti-clockwise direction. Okay, we will try to see an example for that at the end. So right now we have to look at example number 4, which says that if T is a transformation from Rn to Rm, and knowing that it is a linear transformation, we suppose that T of u is mapped onto V. U is mapped onto some vector V. Now we have to show that the negative u will be mapped onto negative V. So we look at it like this. Now because we know that T is linear, so it means T of negative u can be written as negative T of u, because remember, why can I write it? Because negative u can be thought of as negative 1 times u, and now this can be thought of as a scalar. So if you recall, in the linear transformations, T of Cx is equal to C of times Tx. So that this one, T of negative u, I can think of it as T of negative 1 times u, which means negative 1 times T of u, because of linearity of the transformation. But then when I get here, when I say T of negative u is negative of T of u, but T of u is V, so we get negative V. That's what we had to prove, and that's what we have shown.